Thank you for the possibility to do this talk, to spend 1 hour with a love letter to Rust. This is what you can expect. You can expect 3/4 an hour with a lot of code, taking a look why Rust is attractive. This is exactly the talk if you are curious what this Rust is all about and why so many people are eager to learn this new programming language. Before I go into the topic, I would like to introduce myself for those of you who do not know me. My name is Rainer Strobeck, and I'm broadcasting here from a city called Leonding. This is a city near Linz. I'm a passionate programmer for more than 25 years now. I'm also a Microsoft MVP and regional director, but that does not mean that I'm on the payroll of Microsoft, but I do a lot of work in the Microsoft area, especially in the context of the Microsoft Azure Cloud. Professionally, I am a trainer. I am also a part-time teacher, and I'm a mentor at the local Coder Dojo. And that brings me to the last thing, which is really near to my heart, and that is community. I love community work. I'm the chairman of the Coding Club Linz, and we run our local Coder Dojo, which is a programming club for kids. No, we do not program Rust there. My Rust life in terms of community is the Rust Linz meetup, and you are very much invited to join us for one of our upcoming meetups. We do monthly meetups where you can hear talks from speakers all over the world and exchange your ideas, problems, thoughts, whatever regarding Rust in our Discord server. Now, what is my talk today about? You see, I think that choosing a programming language is a little bit like entering a relationship. If you are a professional programmer like I am, you spend a lot of time with the language. You spend this language, this relationship should be a kind of loving and caring relationship. Don't get me wrong, this is not the kind of love that I feel for my spouse or my godchild, but still, it is a kind of love. I have to be passionate about the programming language that I work with. I personally learned coding in the early 90s with Pascal. Then I switched to C and C++, and after that, I switched to .NET and came across languages like TypeScript and Go. And for me, a few months, more than a year ago, 2 years approximately ago, I became curious about this thing called Rust, and I kind of fell in love with the language. And I would like to share in this talk some reasons why I'm so excited about Rust and what I love about Rust. The first question that we have to speak about is, why is Rust so attractive for many developers? Think about how a relationship starts. You meet someone and you feel attraction. Again, it's similar with programming languages. If you are new to Rust, you might ask yourself, why should I invest time? Why should I invest money for books, maybe for trainings and things like that? Does it have a future? Before we go into the technical details, let's discuss this question for a few minutes. The first thing that I would like to mention is Rust is very much appreciated by the community. You are probably familiar with the Stack Overflow Developer Survey, which comes out every year. And in a row from 2016 to 2020, Rust has been the most loved technology in all the Stack Overflow developer surveys. If you take a look at WebAssembly, a technology which really is very exciting in the world of cloud computing, web development, mobile development, then Rust is here really leading the pack. Rust at 26% is the most frequently used language when you develop WebAssembly, according to the State of WebAssembly survey, which came out recently. Very interesting is also that the Linux community is considering to introduce Rust as a new first-class language in the kernel. Let's dive a little bit deeper into that one. Why did the community suggest Rust as a main language in the Linux kernel? They emphasize especially things like memory safety and absence of data races. They think that Rust offers a very strict type system, which offers rich abstractions and lead to a reduction of logic errors. They find it really good for system-level programming that Rust has such a clear distinction between safe and unsafe code. Rust according to them, is a very featureful language, and we will see more about that in the upcoming minutes. Rust has a powerful standard library, which you can use or not use if you are doing, for instance, very low-level system development. The tooling is great. Consider Visual Studio Code, for instance. There are awesome plugins for Visual Studio Code, which make programming Rust a blast. And overall, Rust has leveraged all the experience of systems programming and makes it even better than what you can do today with C and C++. Now, what about the sponsoring? A technology that is great. It will only pay off if you invest in a technology if it's not just great and has a great community, but it also has to have sponsoring to answer the question, will it be there in a few years? Will it be worth my time to invest some time here? And this is definitely the case with Rust. If you take a look at some of the big ones in current IT industry, then take a look at what Microsoft says. Microsoft says that Rust can solve some of the most vexing issues that plague C++ projects. Or if you take a look at Google's security blog, they are praising Rust for its safety guarantees, at the same time while offering equivalent performance to C and C++. Take a look at what Facebook says, for instance. They say that Rust offers the performance of C++ while having a heavy focus again on code safety. Hundreds of developers at Facebook are currently writing millions of lines of Rust. So Rust is definitely in the middle of the core cloud business in the IT world. Rust has organized itself currently in the Rust Foundation. The Rust Foundation is an independent nonprofit organization which leads and steers the Rust programming language ecosystem. And if you take a look at the members, you see that all the big ones are there sponsoring the further development of Rust. So the future of Rust is not only bright in terms of concepts and ideas, but also in terms of the possibilities to bring this power to the street. So from my point of view, Rust is definitely attractive and developers should take a look at it. The main arguments are, as I mentioned, safety, we'll take a look at that, performance, great tooling support, sponsoring by big companies, and a great community and a great open source a track record. Now let's go into the next topic and take a look at the first technical things. I mentioned it quite a few times that Rust offers best-in-class safety and stability, better than even C, C++, or some managed languages. Let's take a look at that and let's take a look what Rust can offer here and how Rust will do it. In this chapter and in the upcoming chapters, you will see a lot of code samples. Please don't focus too much on the details. I only have 45 minutes. So try to get the concept, try to get the big picture out of the code examples. If you want to know really more about it, I share my slide deck with you. And after the talk, if you are as excited about Rust as I am, you can dive into the code snippet and take a look at the details. Before we take a look at Rust's solution to the safety problem, let's take a look at the basic problem. Consider this code sample. It is in C. You have a main method, which calls the getAndProcessData method, which in turn calls the getData method. And there we have a big problem. Because inside the getData method, a memory allocation takes place. And if you take a look, the memory is returned from getData and is never freed inside of getAndProcessData. So we have the problem that we have a memory leak. It's not clear who is responsible for freeing the allocated memory. This is a well-known vulnerability, and I have copied this code into a public repo so you can try it on your own. Of course, I know that modern C++ would never work like that. There are a lot of mechanisms in modern C++ which would make memory handling a lot more safe. But for the sake of this demo, I guarantee you that code like that still exists out there. And if you take a look at public studies, for instance, from Microsoft, they show that for years and years and years, a lot of the vulnerabilities have their roots in memory problems exactly like that. So this is definitely a problem. Another problem is the use after free problem. Again, you see a small code sample here in C. And in this example, we have the problem that in case of an error, memory is deallocated. It's freed. But unfortunately, also in case of an error, the memory is used after it has been freed. That is also a very well-known vulnerability, and it commonly presents a problem to older source code bases. If you think that those problems, like use after free and things like that, are just present in unmanaged languages like C and C++, then you are not completely right. This example is a managed language with a garbage collector. It's written in C#. And in C#, you have the concept of disposing objects that you no longer need. That means you explicitly free memory or free dependencies to memory, and you can write very similar code to what we have seen in C before. So I can dispose an object, in this case, for instance, a connection to a database, and use it afterwards. This will not lead to a security vulnerability, but it will lead to a runtime error, to your software crashing, to your customers complaining, and that's also a problem, definitely. Now let's take a look at the last example before we take a look at the rules of Rust and how Rust solves this problem. Take a look at this source code. In this case, we have the following situation. We have a main method. This main method calls into a print value function, and this print value function receives some memory, and it thinks that it is the job of the print value method to free this memory. Unfortunately, the author of the main method has the same idea, and she is also cleaning up the memory inside the main method. So this is a classical double free problem, which can lead to memory corruption, crashing software, and many other things. A well-known problem, well documented in projects like OWASP, for instance. Again, the double free problem is not just about unmanaged languages. Here you see an example that you might come across when you write code in C# in a managed language with the garbage collector. For performance reason, a language like C# offers so-called memory pools or array pools, where you can get memory for large arrays out of it, and you can return those memory areas later on if you don't no longer need it. Having such a pool should enhance performance because it reduces the amount of memory allocations and therefore the amount of pressure on the garbage collector. And see what can happen here. What can happen here? I can, if I have two developers working on some code areas who are not extremely careful about who owns which memory, both could return some rented memory, some bytes in this case, simply an array of integers. Both can free them or return them to the array pool. And again, we have a double free problem, although we are using a managed language with a garbage collector. So such memory problems are really, really a problem. And endless studies, I mentioned it before, have shown that they lead to code vulnerabilities and to software that is not as stable as it should be. So how does Rust solve exactly that? Rust solves it by specifying a few simple but powerful rules for memory management. First, in Rust, each piece of memory, each variable, like a list, a vector, or a string, or whatever, has an owner. It is assigned to a certain owner. There can only be one owner at a time. And if I allocate some memory, and if I hand this memory over to somebody else, I can give away the ownership. There is always exactly one owner of memory at one particular point in time. You can call it the Highlander effect if you're old enough like me. I know the movie Highlander. There can only be one, and exactly like that it is in Rust with ownership. When the owner, the current owner of a piece of memory goes out of scope, the value will be dropped. That is important. And now comes the most important statement of the entire slide. These ownerships are not just ensured during runtime, but they are enforced by the compiler. That means in Rust, If you write some code and you write code that does not follow the rules that I stated here, the compiler will complain. You will not get a runtime error. And that is pretty powerful. For beginners, it's sometimes hard to work with these rules because you get so many compiler errors. On the other hand, if the compiler says, thumbs up, that's exactly what I want to see, then the code is very likely to really work. Now let's take a look at practical examples in Rust code to understand in details what that means. Here I have a very simple example. If you're not familiar to Rust, let me quickly lead you through this code. In line 2, a new vector, a kind of list of numbers, is allocated. This vector is stored in a variable called numbers. In line 6, we assign numbers to other numbers, and in line 10, we print the content of the vector on the screen. The colon question mark inside the curly braces mean that I want to have debug output. Now let's take a look what's happening with the ownership. First, the variable numbers owns the vector, so the ownership is clear. And now comes the important one. The ownership changes in line 6. In line 6, the ownership goes from numbers to other numbers. The vector is freed when other numbers goes out of scope, and that happens in line 12. So if you would try to access numbers in line 11 as shown here, this will lead to an error. But not just to a runtime error, but this will lead to a compile time error. It's simply not allowed. Ownership has changed. Numbers does no longer own the memory. Therefore, you cannot access the vector through numbers. If that wouldn't be the case, then Rust would try to free both numbers and other numbers, but both variables point to the same area in memory, and we would have a double free problem. And that is prevented by Rust's ownership rules and the compiler. Of course, if you take a look at this little bit extended and changed example of what we saw before, it is possible to clone memory. In this case, we clone the other numbers into cloned numbers. Then we have two different owners, but we also have two different areas in memory. So it isn't a problem that we now have two owners, and therefore it's perfectly fine. Take a look at line 16, that we access cloned numbers and other numbers. So cloning is perfectly okay. Let's take a look at another sample, and this sample is about ownership and functions. Let's again start at the very top. Take a look at line 2. Again, we allocate a vector and store it in a variable called numbers. But then recognize what we do in line 3. In line 3, we give the vector owned by numbers to a method which is called consume. So the ownership changes. The ownership goes into the method consume, and now numbers belong to the function consume. When the local variable numbers goes out of scope, the vector is freed. It is not possible to access numbers in the main method after the call to consume. So we have a transfer of the ownership between the main method and the consume method. And again, we have the rule valid. We only can have one owner at one exactly point in time. Now let's take a look at the other side. Here we have a function which is called produce. And as you can see in line 16, this function produces a vector. So it allocates a vector in line 17, pushes some numbers into this vector, and returns the number. For those of you who are not that familiar with Rust, line 19 does not contain a return statement, but please note that the line 19 does not have a semicolon at the end of the line. That means it is the returned value from the function. This is the syntax of Rust. So by returning numbers and the vector, the ownership moves to the main method. Now the main method has the ownership and stores the vector in produced numbers. And then we can print produced numbers, and when produced numbers goes out of scope, the memory is freed. We have one owner at one particular point in time. What about borrowing? Borrowing means that a method allocates some memory, and it would like to hand over control over this memory for a limited amount of time to another function. And that is the case in our consume function, because our consume function is only reading memory from the vector. It doesn't need ownership. It just needs to be able to read from the vector. And the good news is that you can borrow, read-only borrow a single piece of memory to multiple functions. Take a look at this function here. The big difference is that this function now gets a reference to the vector, and that is called borrowing. So numbers is read-only. We can read it. In this case, we are using an iterator and an aggregation function to calculate the sum of the values that are stored inside of the vector. It is read-only because it's only a reference to vector. It's not explicitly marked as being mutable, and therefore line 14 is not possible. What I want to emphasize here is that the consume function now just borrows the vector, and you can have multiple other functions have a read-only borrow on the vector. That's important. Now, if we take a look at the second function, add and consume, it is important to see that this time the function also gets a reference to the vector, but it gets a mutable reference to the vector, and therefore the borrow mutable, there can also be just one mutable borrow, but still it is a borrow. So the main method still has the ownership of the numbers. But for a limited amount of time, add and consume can read and write to the vector, as you can see in line 20, where I push the value 42 into the vector. As I said, the main method is still the owner, so we can at the end print the resulting content of the vector, and Rust will automatically free the vector. It is absolutely clear that it can free the vector at the end of the main method, because the main method and the variable numbers owns the vector. Let's take a look at another example, which is pretty common when you write code. Let me quickly lead you through this example. This time, we are taking a look at an async function. Please take a look at line 9, which is an async main method. And please take a look at line 20, the sum method. As you can see, the async main method in line 10 allocates again a vector and then calls the sum method. But the sum method has some wait statements in it. If you take a look at line 22, you will see a delay statement with the await functionality. That means we are simulating some harder work, which takes 2 seconds to calculate some difficult mathematical formula on the numbers. In this case, I'm just simulating some work by waiting for 2 seconds. And at the end of the day, I'm returning the sum over the numbers. But the method sum will be active for at least 2 seconds. And if you take a look in line 12, while the sum method runs, we add something to the numbers. And that is not possible in Rust. It would break the iterator, and it would break our ownership rules. We cannot borrow the vector, and on the other hand, borrow the mutable vector to the add method at the same point in time. It's not possible. The big thing here is Rust will give you a compile time error if you do something like that. The same code in C# in a managed language with the garbage collector would look like that. I will not go into the details because even if you have not written C# before, you will probably be able to read and understand the code from the context. But the point here is that in line 10, I do exactly what this example shows in Rust. I add a number, 13 in this case, to this list of integers, while in line 14, the method sumAsync is still running. And that will again result in an error, but not in a compile time error, but in a runtime error. And that's the big thing in Rust. So Rust can really solve a lot of the problems here. Let's take a look at the last, more complicated example. This example works with so-called channels. Take a look at line 6. I'm creating a channel of integers here, and I would like to solve a producer-consumer problem. So I'm spawning in line 8 a producer thread, and this thread pumps some values, in this case just some integer values, into this channel, and between each channel, between each send operation, we wait for 500 milliseconds. That's the producer. And please take a look at the move keyword here. The move keyword means that the captured variable, in this case the sender variable, which we get from the channel in line 6, is moved. The ownership is moved into the Lambda function of the thread. So there can only be just one sender inside the producer thread. But if you take a look at the bottom, this is the receiver part of the channel. You see, the receiver part was generated by producing the channel in line 6. Now we can safely call receiver.receive and match over the result and print the result once we got something. If you are new to Rust and you wonder, hey, what's this match all about and what's this okay and error, please be patient for another few minutes. You will learn more about it. So as you can see, the borrowing rules also apply to more complicated multi-threaded programming scenarios where you have sender and receiver running in different threads. So what can we summarize? Rust is really stable and safe. It has clear ownership rules, and the important thing that you should remember from this talk is those ownership rules are enforced by the compiler. Of course, sometimes things are not that simple. If you explicitly want to have shared memory with multiple pieces of code accessing, reading, and writing a certain element of memory, of course this is possible in Rust, of course. But this should be the exception and not the rule. For the typical everyday programming, Rust is this iron safety net underneath you that makes sure that you don't screw anything up like it could happen in C or C++. That leads to less runtime errors, very important thing, but even more important if you think about systems programming, about long running, for instance, microservices running in the cloud, less vulnerabilities. There is a second aspect here in this enforcing of the rules by the compiler, and that's about performance. Because the compiler enforces so many strict rules, it can optimize the code to a very large extent without being afraid to break something. So the performance is simply awesome. A managed language that has to do all these checks at runtime obviously needs CPU cycles for doing the checks. Here, the checks are at compile time and not at runtime. Good. As you can see, my relationship, my love to Rust is based on a feeling of security and safety. That's great for a loving and caring relationship. The next topic is about deepness. A relationship that I would like to have with a programming language should be deep. I want to have a deep type system. I would like to have the language to support myself, to make the best out of my ideas, to offer me great abstractions and things like that. So for the next few minutes, I would like to walk you through some examples, some small examples about the type system in Rust, so you understand better how you create abstractions, doing structured programming and things like that with Rust. First, Rust has no classes. So if you come from programming languages like Java, C#, TypeScript, and so on, you obviously think that Rust will have something like classes, inheritance, polymorphism, and things like that. I'm afraid not. Rust has structs. Structs is the basic building block of creating data structures in Rust. And here you have 3 examples for structures. Structures with basic data types like float32, and also composed structures like rectangle and circle. If you want to work with these structs, it's obviously clear that you can create instances of these structs, as you can see in line 3. But it's also possible to create duplicates and copy parts of another struct into a new instance of the struct with a dot syntax, as you can see here in line 6. Isn't that beautiful syntax? I love this syntax. I'm also doing a lot of work in the C# area, and there you have this with clause. It only came recently to C#, but Rust has it built in for quite a while. Another example that is worth mentioning is this one. By default, variables in Rust are immutable. So line 3 and line 6 create immutable points. If you want to be able to mutate a variable or its content, you have to declare it as being mutable, like you can see in line 10. Then and only then I can change the content of the rectangle that I create in line 10. All the examples above created instances of the structs on the stack. But obviously, you can create instances on the heap too. And for that, Rust offers a lot of different data types, like, for instance, box. In this case, box new would create an instance of, in this case, the circle, create the circle on the heap, and return a reference to the heap into your variable C, which again is marked as being mutable. Therefore, in line 17, we can change the radius of the circle. So that is structs. Let's take a look at functions. You've already seen that in Rust, you can simply create standalone functions. Functions that have no relation to any kind of data structure, but you can also add implementations to structs by adding functions to a struct. Please take a look at line 1. You see we have the implementation of the rectangle struct that you saw before, and line 15 shows you that there is, or there can be, a function area which gets a borrowed reference to self, meaning the rectangle, and therefore you can read from self by calculating the area by multiplying with height. Enlarge is another example of a bound function, a function bound to the structure rectangle. In this case, it gets a mutable borrow of itself, and therefore we can change the content of the rectangle in place. So we can, in line 11 and 12, change the x and y coordinates by doing some multiplication, some basic math. I think you get the point here. On the right-hand side, you see that you need to allocate a mutable rectangle in order to be able to call enlarge, because otherwise you couldn't borrow a mutable reference to the enlarge function. The second example here is circle. And circle contains, as you can see it here, a kind of constructor function. Unit circle gives you a new instance of circle by creating it. That is the analogy to a constructor in other languages. There isn't a notion like a constructor in structs. You create such constructor functions and you can use them to instantiate, in this case, a circle, so an instance of the struct. On the right-hand side, in line 1, you see how unit circle is used. Once you discovered structs, the next thing that you have to understand with Rust is traits. If you know interfaces from other languages, you have a rough idea about what traits can be. Traits, like in line 1, are kind of collections of functions that have to be implemented by a struct in order to implement the trait. In this example, I created the area trait, which requires the existence of an area function, which borrows an instance of the object and returns the calculated area as a float 32-bit. And then in line 5, you see how I implement the area trait for the rectangle by saying implement area for rect. Of course, I can also implement area for circle, as you can see it in line 11 and further. Now let's take a look at how we can use traits. On the right-hand side, you see that I create a shape with area and assign it to a reference of a rectangle. And the important thing is the dynamic reference in line 5. You see it here in the yellow rectangle. That means that the resolution of the functions is done dynamically based on the underlying type. So area from rectangle is called if shape with area is a rectangle. Circle.area is called if it is a circle. Of course, you can also use it with vectors, for instance. In this case, I am allocating a vector of area objects, and then I'm pushing a reference to a rectangle and a reference to the circle on the heap directly in the vector. That's interesting because you see here that I can push a reference to something living on the stack and something living on the heap into a vector and then consume it in a for loop, as you can see in line 12. So this is what basic traits are all about. But traits in Rust are used all over the place. And here you see two important system traits that you have that are great to describe the concept of traits and how it is used in the base library, in the standard library of Rust. Take a look at the display trait. The display trait was not defined by me, but it is defined by the Rust standard library. I can implement it for a data structure like point. To make a long story short, in display, I have to provide a text representation for my data structure. Please take a look in line 13. Here I'm just building a text representation with some JSON-like data structures and implement the display trait with that. And therefore, I can, take a look at the bottom in line 2, use the print line macro, you will see macros in a second, to display the origin, which is a point. And the print line macro will use the display trait to turn my struct into a string. Another example is the add trait. It is a generic trait. It allows me to define the behavior which should be executed when I add 2 points. You see the business logic in line 6. Down below in line 3, you see what is the result of implementing the system add trait. The result is that I can use the operator plus to add 2 points. So you can see that traits are really a basic, a foundational building block of the type system of Rust. Now you have seen multiple times these exclamation marks at the end of some words, like vec exclamation mark or print line exclamation mark. Macros are behind that. Macros can exist as you can see here on top of the struct point here. And this macro is an example to auto-generate an implementation of a trait for the structure. Don't get me wrong, you cannot just use macros for implementing traits. You can use macros to generate code that does anything that comes to your mind. In this case, I'm using the system derive macro, telling the system to auto-generate the so-called debug trait. And the debug trait will make sure that I can use debug output for my structure. And in this case, it will just take the elements of my point, which are 2 basic data types like floats. So just data types which also implement the debug trait to generate another higher abstraction level debug trait for me automatically. I do not need to write code. This is done during compile time, not during runtime, the code generation here. So this is an alternative to what in many managed languages is done through reflection, for instance. Or this example here, you've seen this before. This whack exclamation mark is a macro that makes it easier to create a vector of things. And therefore, if you do that, you can use the print line macro, which will care for displaying the formatted output as specified here in line 5 on standard out. You do not need to write many lines of code to print something formatted on the screen. You can just use a macro for it. So macros are, again, very important. The next thing that I would like to speak about are enums. I guess you know what enums are from languages like Java, like C# or TypeScript. But enums in Rust are more powerful because enums, as you can see in line 8 and 9, can have values. So think about poker moves. I don't know if you play poker or if you ever played poker, but in poker, it is possible to call a hand. That means you have to place the same amount of money into the pot that is already in the pot, or you can raise. So you have to put even more money into the pot. And as you can see here, the enum poker move contains a fold, means I'm stopping, I'm no longer playing, calling and raising get parameters to the enum. That's a special case for enums in Rust. And enums are also exactly as powerful as structs are. They can implement traits and things like that. Enums are additionally deeply integrated into the rest of the language. Take a look at the match statement here. The match statement allows you to specify all possible values of the enum, and Rust will make sure that you do not forget a single value that is possible in the enum. So if you don't have the line 5 default value here, it would raise a compile time exception because you have to specify a defined behavior for every value of the enum. You cannot forget anything. Again, that's a question of safetiness. Enums are widely used inside the standard library. For instance, I would like to point out the option enum. It's part of the Rust standard library, and it is the replacement of null. By default, if you're not using some unsafe pointer magic, by default, a variable in Rust cannot be null. It is not possible. But at some point, you maybe have to represent that a variable has a value or doesn't have a value. And here, a good example is the option enum. Option, as you can see in line 11 and 12, can have two different values, either none, if it doesn't have a value, or some with a value parameter, if it has a value. And here in this example, I'm using an iterator to get the fifth element, it's zero-based, from an iterator. If it finds a value, I go into the sum part of my program, found a move. If it doesn't find a move inside the vector, it enters the none part of the match clause. So as you can see here, this is obviously often used inside the standard library. Also the result, the optional result of a function, which can either be a result or an error, is represented by an enum. The result enum is frequently used. The result enum can either be okay with the resulting data, in this case, it read some string, some data from a file, or the error thing here, which will represent the error that happens when accessing the file main.rs in this example. So you see, enums are also a building block of the core type system of Rust. So to make a long story short, Rust has deepness. It has powerful, feature-rich type system. It has a lot of built-in types like basic data types, standalone functions, things like that. But it has structs, enums, traits, and macros as the foundation for building powerful class libraries, applications, standard libraries, whatever you want to build. And then there are so many small traits. As a developer, I sometimes love this small, little, simple things which really make my life easier. I will go very quickly to some of the things so you see that the reason why I really love to use Rust. So let's take a look at the first trait. The first trait, as I mentioned before, is mutables, shadowing, and freezing. Take a look at line 1. We get a location which is a reference to a string. It can either be a string or a string slice or something like this. But notice that inside the function, I also define a variable called location. In many other languages, that would be an error, but not in Rust. In Rust, we are shadowing the existing variable. We are redefining the variable and give it a new type. It still is type safe, but it shadows, it hides the original meaning of location. And that can be used for some pretty powerful thing. Think of, you have a mutable value, and for some area in your code, you would like to freeze this value. So you can open a code block like shown here, assign the mutable value to an immutable value, and suddenly inside the code block, the value is frozen. You cannot accidentally assign a value to it. When you leave the code block, take a look at line 14, you can assign something to the value again. Beautiful, isn't it? Mutability, shadowing, and freezing. Or error propagation. Take a look at this small question mark here. In this case, I'm writing a helper method called read data, and this read data uses file open in the background. File open obviously returns a result, and it can result in an error. And by adding the question mark at the end, I'm telling Rust, hey Rust, if there is an error, take the error and return it as an error result from me, from the method read data that I'm currently implementing. It's called error propagation. Beautiful, isn't it? Nice to write. Or another thing, in this case, I want you to focus not on the code, but I want you to focus on the comments. Can you see the example section in the comments here? Believe it or not, that's executable Rust code. In Rust, you can add examples to the docs and you can test the code. Take a look at the screenshot in the right lower corner. You can see that I call cargo, which is the build tool of Rust, cargo test doc, and it will execute the code inside of the documentation and also make sure that it doesn't panic, so you can add some kind of assertions just like unit tests. Speaking of unit tests, obviously, Rust has a concept of unit tests. Here you see just a simple example, but you have to take a look into the documentation to read more about it. Another quick one, and then we have to come to an end, is type inference. Do you see line 2? We create the vector of, well, we have no idea. We just create a vector and ask Rust to figure out the type of the vector later on. It takes a look at line 4 and says, oh, Rainer is pushing an integer 32-bit into the vector, so I understand that this vector now has the type integer 32. So I cannot push a string value into this vector. These were just a few treats that I wanted to show you that stand exemplary for why I really love to use Rust and why I think Rust is a great language. Did you get curious? We only had 45 minutes for this quick talk, and I promised you that I tell you why I wrote this love letter to Rust. If you are curious, if you think that maybe this is a loving and caring relationship for you for Rust and for Rust for you, then you might take a look at these options. You have gotten, I think, the link to my slides already in the chat. Rust has a great Rust book, which is available for free online. Just click on the link and you have the book. Just install Rust and start coding. The best way of learning a programming language is by practicing it. There is also a great website, which is called Exorcism, with lots and lots of small examples, which allow you to make a gradual step-by-step entry into this new language. You can visit a meetup, and I couldn't resist to add a link to our own Rust Linz meetup, where I'm one of the founder and hosts of. So if you would like to visit us, talk with peers about Rust, follow this link. And last but not least, I also added a link to a conference where you can learn more about various topics about Rust. And with that, I say thank you very much for attending this session.